Thank you very much for coming. So today's the fourth lecture about the Dubois property and consequences. And so you haven't been here for the first three, so it's basically a new start. I mean, everything is motivated by its applications to these moduli questions. But I want to focus on what are Dubois singularities and how to use them, and hopefully you will find them useful in some context. But before that, let's start with some examples. And so you see and D are smooth projective curves of genus at least 2. And then I take the product of them, C cross D. And I take a line bundle on it, which is a full sum ample bundles plus back from the two factors, tensor them together. So these are the simplest ample line bundles you can write down on the product. And then I look at the cone over. Okay, so this XLM is the cone over C cross D with normal bundle the back, bundle the box product of L and M. And now it's easy to write down the dualizing sheaf, that's just a sheaf that corresponds to, well, not surprisingly, so here I have the dualizing sheaf of C cross D, and then I just have to tensor it at the sheaf corresponding to it. And so, now then I will choose the degree of the first line bundle L to lie between G minus 1 and 2G minus 2. Okay? And so then what I will do, I will fix M, and I'll let here L varies through all the line bundles of this degree. So then I get the family of cones parametrized by the degree D component of the Picard. And then on the next slide, I will show you that I can choose this M in such a way that the cones form a flat family, but the dualizing sheaves are not. And then for different choice of M, I will see that the dualizing sheaves, they form a flat family, but the cones themselves are not. Okay? So it's just so interesting to see that the flatness of these two objects are in fact independent of each other if you write down the right example. Okay, so it's probably easier to see here before we go to the next slides how to guarantee that these are flat. But if all of these dimensions they are constant, so if I vary L, I get these vector spaces, and if all of them have the same dimension, that is XLM is a flat family. And then the same for the dualizing sheaf. If all these dimensions here are independent of L, so once again I fix M and I let L vary. So if I get something that's in the dependent of L, then the dualizing sheaf is flat. So, and now the point is here, this choice of D between G minus 1 and 2G minus 2, it says, so for instance, if you look here, then it says that as soon as this M is at least 2, then I got this L square that's over 2G minus 2, so that means there's no H1, so there's no dependence of L. And now in the dualizing sheaf, I'm sort of going in the negative direction. So see here, this M can be minus 1. If it's minus 2, then here in this factor, omega c tensor L minus 2, that has negative degrees, so I do not get anything. So here the only interesting thing is that can vary is M equals minus 1. So this is the only reason I chose this. I could go down to 1, but there would be finitely many of these that I would have to compute. But so with this range, it is easy that sort of these vector space. So these numbers depend on L only for m equals 1. As I said, only H0 CL, and then it indeed varies. And then here, omega C tensor L minus, which means that that was OX, and here the only summand that sort of might change is this one. And then for omega, the only summand that might change is this one. The second part is constant. I'm not varying m. So, okay, so then, well, this varies. But how can this tensor product be constant? Well, if this H0 does 0, okay? So that if I choose m, for instance, to have some small degree, or just 1, then I can achieve that this is 0, but this one is non-zero, yeah? So that this one will have degree 2g minus 2. And so that way, here the cones will be flat, but the dualizing sheaves are. On the other hand, if I choose m to have degree, say, what is 2g minus 1, then this is non-zero, but I can achieve that this one. So this one is 0. And the cones themselves don't form a flat family, but the dualizing sheaf, okay? And so actually the second may be the more surprising that it can happen, that in a non-flat family, the dualizing sheaves are indeed flat. And this is maybe the more surprising, and this will come into play for us. Okay, so then here to summarize what I already said. So this is just an example so then, well, when is the dualizing sheaf flat? So, well, if you start with the proper variety of dimension n, and L is ample, then, well, this omega dualizing sheaf is just the sheaf associated to this graded ring, okay? Now, these H0s, they are just dual to H and X L minus M. That means if I have a projective morphism of relative dimension n, and this L is relatively ample, then omega is flat and commutes with base changes if and only if these higher direct images are free. Well, so I don't need them for all m because I take the price. So if the first few are messed up, it does not hurt me, but so this is in fact an equivalent statement. Okay? So that means that I need the largest, just push forward. This is the largest that can exist. Okay? And so then there are two principles that sort of work here. So there's a more general statement. I just showed you sort of the simplest version here. So this has a dot. So this is the dualizing complex. Okay. So that said that the whole dualizing complex is encoded in the cohomology group of negative powers of all ample line values. So if you understand everything about these, that's well, okay. I don't want to go too far, but maybe you can compute at least all the cohomology groups of these, but maybe more. So this negative power, they tell you a lot. And now the other thing that I found maybe even more useful in my life is sort of this, which I can recommend to everyone. Okay. Yeah. Okay, so now this is a detour. I will use this construction of cyclic covers. So I believe many of you have seen that, but let's just go through that. So I start with with a variety. It doesn't have to be projective for what's happening here, and then I have a section of this M spire. So L is a rank 1 reflexive sheaf, and this is I take the M tensor power, and then it's WL to make sure that it's reflexive. Let's assume that X is normal or the S2 or something like that. I think I will apply this in some cases where this is projective over some Artinian base. So maybe let's assume only that this is S2, okay? And so then I can take the m's root out of S. There are two ways. Either I take the spec of this algebra. Okay, so for instance, if I want to take the product of these two, then L inverse time L to the 1 minus m, I just tensor them together, L to minus m, and the section exactly sends L to minus m to O. So this is the way you take the product. Or you can take it actually, you take the whole spec, so that's a line bundle, and then its S will be the function here, I just look at the zeros. So you can contemplate these two descriptions like this. Now, then if I look at this and then I take the dualizing sheaf and I push it forward, then it is just the dual, that I have to home this into omega. So this bracketed tensor power means is neither of these is assumed locally free. The tensor power might be bad, so I take the tensor power and then it's reflexive power. Okay? Or maybe it's easier to think of it in all the applications, both omega and L will be locally free outside the codimension 2 sets. So I just do this construction outside the codimension 2 set where everything is a line bundle, and then I just push forward everything. Okay.
What's the direct sum? What is the plus?
Huh?
What's the direct sum?
What this?
No, like downstairs there's a plus.
Here. Yes, direct sum. Thank you. Yeah. Okay. So that's especially useful whereas L is omega x itself, because then the push forward of omega will be just the powers of omega x. And so the main point of this is that if I have some way of getting information about the dualizing sheaf itself, but I would like to have information about the powers of the dualizing sheaf, then so this is the formula that, well, I have to pass to a cyclic cover and hopefully understand the dualizing sheaf, but that will tell me information about all the powers of the dualizing sheaf downstairs. So this will be very, very useful. Okay, and so for instance, it says, to go back, if L is ample, or the line bundle, then L inverse is direct sum and the push forward of O. Okay, so that means that this cohomology group is just the direct summand of it. And so if you imagine now X or L, it varies in a family, then if I can prove that the cohomology groups of these are, the dimensions are independent, then it also implies that the dimensions of these do not change if I move in my family. So, and then similarly, if omega x happens to be ample, then the cohomology groups of the powers of omega, they are the direct summand of the cohomology groups of omega itself in a cyclic cover. So that means that if I'm interested in negative powers of ample line bundles, or in the powers of omega x, if I can just pass from x to the cyclic cover, and I can prove something here about the structural sheaf or about the dualizing sheaf, then downstairs I get information for all ample line bundles, negative powers, or about all the powers of omega, how it's called, groups. Okay, and so now let's make it into a formal statement. So let S be a class of singularities. I take two very minor assumptions. So one is that if X has singularities in X, then if I multiply it with A1, then it still has singularities in X. And the other is that the general hyperplane section. And so if X has singularities in X, then so is the general hyperplane section. And so this holds probably any class of singularities that you heard about, maybe not. This holds for many. Now this means that the general cyclic cover also has singularities on X. Remember that the second way I described the cyclic cover, I just took a line bundle over the base X, and the general section there. Okay, so but the line bundle is taken care of by first one, and the general hyperplane section by this. Okay, and now this is exactly what we need because I'm interested in X, but for computations I needed this cyclic cover. Okay, and so this means that if S satisfies this, then the following are equivalent. That is, R and G lower side L2 minus M is locally free for all ample L, and so the whole flat projective morphism whose fibers have singularities on S. Or that it is just the highest push forward of the structure sheaf is locally free. Okay, so it's really nice because these are some. Well, I don't know what are the ample line bundles, so these might be hard, but it seems that if I just compute something for the structure sheaf with all these singularities, then I get some information about all the negative parts of line bundle. And as I mentioned before, if I understand these, then I understand the dualizing sheaf. Okay, so this is the somewhat roundabout way, but this is how we will prove that the dualizing sheaves in our cases are. Okay, so let's see, well, how to check that the HIX OX are flat. Okay, so when you look at the cohomology and base change theorem, so it's enough to do it over R linear basis, well, let's say residue with K, and I have something flat and proper. Then the second equivalent that all the HI XA OXA are free A modules. Okay, so I mean, so since Artinian being flat is the same as free, or that these are surjective. So I emphasize that surjectivity I need here only when I pass to the closed point, not smaller scheme. It's implied by this, but it's enough to check this for this scheme. Well, let's just illustrate this. When I have this K epsilon, so epsilon square is 0, I have this exact sequence. And so I need that. And then you see that this map, I assume, is surjective, which means that this map is injective, and this map is surjective. So indeed, the dimension of this is twice the dimension of what I have here. These are the same, and that's exactly what I want. And so, based on this, you write on the same sequence, you induct it out for the length of the Artinian scheme. It's okay. Okay, now, so what are Dubois singularities? And, okay, so the definition that I like to live with, so that if I have something proper and the Dubois singularities, then, well, so then I definitely have to be over C, because here I want the topological cohomology of the constant sheaf. So this is topological cohomology. It maps surjectively on the sheaf cohomology. So now, besides this, I will use two properties of Dubois singularities. Well, and so if X has Dubois singularities and multiplied with something smooth, it also has Dubois singularities, and the general hyperplane section also so has Dubois singularities. For a long time I have been trying to prove that these properties, these three properties are listed here, in fact imply that X has Dubois singularities. It is not clear, but so pretty much all the proofs that I did with Dubois singularities, they started with pretending that these three are enough, and then try to work with them. There's only one problem, that this really needs X to be proper, this surjectivity. And so if you would like to prove a local statement, which you sometimes would, then you will need a local version. And here I always use my second principle that I mentioned. Just ask Sándor Kovács, and then he supplies it. At the end of the lecture, I will more or less explain what the right definition of the Dubois singularity is.
I have a question. So which morphism are you referring to here? Like HISC match here, like.
Well, and so this is naturally a subsheaf.
I see.
Yeah. So I mean, the constant functions, they are holomorphic.
Yeah.
Okay, so I think I sort of skipped something that by Serre, the algebraic sheaf cohomology group is the same as the analytic group. So yeah, so I suppose I should have set it here HIN. So it's a holomorphic the cohomology group here. Okay. Yes. Thank you. Yeah. Okay. So now this whole thing started well with an earlier paper of Dubois, but there is this paper. So that the central fiber has Dubois singularities, then an Artinian scheme, but then the cohomology group of the total scheme surjects into the cohomology group of the central fiber. And you see, this is precisely what we needed to show that the push forwards are locally free. And now, well, amazingly, this is the proof. Okay, so I just write down. So I have this natural map for the whole scheme, so the constant map here, and then I have this here, and then these are just the restriction morphisms. Yeah? I would like to prove that this is surjective. Okay. Now the Dubois property says that this map is surjective. Yeah. Now what about this? Well, the point is that the constant sheaf does not see the nilpotent. Okay. So that means that this is simply an isomorphism at the cohomology level. So that means that this map is surjective, and then of course I can go this way. I have to have a surjectivity. Okay. So now, okay. So now of course I would like to apply this to the semi-log canonical singularities. And so if you haven't been here, let me just recall them, or even if you have been here and you don't exactly remember everything, I don't think I will need much. So the thing is, if I have canonical models and I want to compactify the moduli space, then I have some worst singularities. So for curves, the interior of the moduli space smooth curves, but the boundary of the moduli space that has nodes. So basically you can think of this semi-log canonical as the higher dimensional generalization of node. And so it has these three properties that at least in codimension 1 I have only only nodes, so that sort of comes from curves. And I keep S2 the Serre property S2. And now then I assume that some power of omega m is locally free. So let sigma m denote a local section of it. So you see, the sigma is then defined maybe only after root of unity, but it will not matter too much for us. And now then the key property is, well, there are three equivalent versions. Like I use resolution, that if I look at the y2x is a resolution, the canonical class upstairs, and the pullback of the canonical class. Well, plus effective, you see for smooth things this much happen. But now I allow simple poles, okay? So A is the reduced device. So then equivalent formulation is that you can pull back the powers of the dualizing sheaf, again, with simple poles. So for the R's power, of course I can R4 pole. And now, then if you try to do differential geometry on it, then this is the right property. That is the sigma wedge sigma bar, and this undetermined root of unity goes away here, so that this is actually a well-defined top form. You can integrate it. Then, well, this integral, this might be infinite, but just sort of barely. So if you just help yourself a little bit with some small part of a function that vanishes on the singularities, then it becomes a finite integral. Okay, and now the main theorem. I don't want to prove this here, but just handle it as a black box that semi-log canonical implies Dubois. So that's why I'm interested in Dubois singularities, because then the boundary of the moduli space I have this. And so now, putting together everything, we get the corollary that if I have a flat, maybe it should be pro-paramorphism, with pi bears have these semi-log canonical singularities, then the previous arguments show that omega x over s is flat over s and commute with base change. Okay, so at least the dualizing sheet, which is somehow a basic object, I mean, that's what I want to be ample, that they form at least a flat family. So I don't have to worry about getting some embedded points. Okay, now what about the other powers? Okay, and so from what I said so far, it would seem that sort of this comes out automatically, but let me explain that in fact it does not. So let's start with the case when S is reduced and say the m's power of the relative dualizing sheet is locally free for some m. Yeah, I think I probably left out the assumptions that the fibers have the semi-log canonical singularities. So then I say that all the other powers are flat over the base and commute with base change. Okay. Now I want to do a slightly similar case where the base is in fact a smooth curve, and then, well, just by passing to a small set, I may assume that m's power of omega x over c is not just locally free, but free. Because then it has a nice constant nowhere vanishing section, so I can take the nice cyclic cover out of it. And there is at least in retrospect, fairly simple lemma of Reed that the cyclic cover also has log canonical singularity. Or maybe I should say semi-log canonical, since that's what I assume. Now, then there is a sort of longer story here, which started with Elkic, that Elkic proved that canonical singularities, they are rational. And so then it is easy to out of that if I just do slightly better than log canonical, it's called log terminal, they are also rational. But log canonical singularity is not exactly that, but if you sort of squeeze the proof enough, then you get that at least the dualizing sheet, that the fibers are satisfied by Serre's S2 condition. Okay. Now then, so we did this already, that the other powers of the relative dualizing sheet, they are direct summands of this. Okay. So that means that the fibers, they also satisfy Serre's S2 condition. And so that's exactly means that they are reflexive. Okay, so then the fibers of these they are exactly this. So you see the general, even if you know there's omega x over c, of course it restricts to the omega of the fiber. And if you take tensor product, well, there is at least a surjection, but as soon as you dualize, then you lose this isomorphism in general. So this is something that we need to prove by hand. So this works when S is reduced. Okay. And so now, if we go back to the definition of stable morphism, it included this assumption that all the reflexive powers of X over B, they are flat and commutative based. Now, we just checked that this is okay over a smooth curve, that this is implied by the rest of assumption. And then you work a little bit, then out of this you can get that over reduced basis, this in fact works out. But over a general basis, this is not an implication that we have. Maybe it's on the next slide. Yes. So with Klaus Altmann, we worked out what happens with cyclic quotient singularities just of surfaces, and not for all of them, but there are many cyclic quotients where the first order, the deformations, there is some power of the relative dualizing sheaf is free, but essentially none of the others are free. Okay, so there are just two. But for zero, I mean, it doesn't matter. The other is just the omega tensor did something free, so that's plus omega is free, and this is okay. So that means that the previous result, so the once we know something for omega, then it holds for all powers. It does not work over non-reduced space. Okay? So that means that this assumption we had over arbitrary bases, it must be added by hand already for families of surfaces, already with some of the simplest singularities. I mean, we have the simplest surface singularities that you can imagine. Let's see, are there any questions here? Okay, and so then let's move ahead. So we did these computations for surfaces. Now you might ask, what happens if I do higher dimensional quotients, so for example, quotients of C3? Well, in the isolated singularities, there is an old result, so the Schlesinger, that says that they are rigid. Okay, so that means there's nothing to do there, but there are plenty of semi-low-canonical singularities with interesting deformations. But a fairly recent result says that, in fact, the stability condition is automatic once you are in codimensions. So that if I have this, so to be precise, so that assume that I have a morphism that is flat and of finite type. And we assume that the fibers are semi-low-canonical, and the morphism has this local stability condition in codimension less than or equal to in each fiber. Then the morphism is in fact locally stable. Now, I prove something slightly stronger. Even the semi-low-canonical I need only in codimension at most two, but there's a slightly more precise statement. Okay, so it sort of says that the surfaces are the hardest case if you want to understand the moduli. So there's a lot of things that you have to do by hand for surfaces, but so the once you did surfaces, then the higher one-dimensional theory somehow just rolls along automatically without any extra conditions that you have to impose by hand. So I know that's how it is, and so let's see how can we prove something like this. Okay, so maybe I should say one of the big questions I have, and so I have not said much about pairs, but I think many of you have seen there are moduli of pairs. I don't know whether the same state matrix 2 4 factors. So if you can find a counterexample or you have some proofs, I would be very interested. So in some cases, when delta, all the coefficients are 1, then it's easy to reduce it to this case, so that's okay. But if there's some random coefficients, and I really don't know what happens here. But it would be nice to show, because I mean, so partly because we know much less about higher codimension singularities. So the codimension one, you have only nodes. Of course, nodes have only one deformation. Nothing interesting happens there. And then in codimension 2, I have the surface singularities where we have a complete list of them, and essentially we have a complete description of the deformation spaces. So it really says that somehow we have to check for this moduli purposes only the singularities that we have an easy way of understanding. It should be a very nice thing to do. Okay.
So before you were mentioning rigidity of quotient.
Yes.
What is the relation between this rigidity with the theorem that you mentioned before? Because that's another. It's not an obstruction to deformation. It's something that concerns at the base. This other statement, no?
And so for instance, if I have a typical quotient singularity, okay, then there's deformation space with lots of irreducible components, but at most one of them is the semi-stable deformation. Okay, so there I have to sort of throw away sort of things by hand. There are lots of deformations that are not semi-stable. This omega power condition is not semi-stable. But it says that, so for instance, it says that the same thing does not happen if the singular set has codimension 3. Okay? Then it says that automatically every deformation of it will satisfy this stability condition. And so sort of more generally, if I have some singularity codimension 2, then it's only at codimension 2 points I have to check that this omega x2m locally free condition holds. At all the other points, it just happens automatically. Okay? And so even over Artin schemes, I mean, that's the thing. So the surfaces over Artin schemes is sort of very messy when this condition is holds.
So you have to deform into the Artin component of the rational.
No, the Artin component is the worst.
Is the worst.
Yes. Artin component is the worst. But that's where it does not happen at all. Yeah.
So, like, which components are okay?
Well, and so, okay, yeah. And so okay, so how can you write down easily some deformations or some quotient singularity? Well, you know that the vast singularities xy plus z to n, we have these deformations. You can add sort of lower terms, okay? And now, if you can just cook up here some group action where this is equivalent, okay? So say for instance, you take the quotient of them, for instance, the R root of unity, you X, for instance, 1 here, minus 1 here, and maybe this is a multiple of R, then you can put anything here. And then here you can take the powers of r, okay? So you cannot take anything but this x at the very end, but you can take e1 times e to the n minus 1 times r plus n. And the theorem says that these are all. These are all the deformations that lead to stable families. Okay. Okay. Any other questions? Okay. And so here is the key theorem. Well, I still need to get back to the dualizing sheaf. I would like it to be flat and commutes with base change. And so before that, I proved that if all the fibers have Dubois singularities, then omega x over b is flat and commutes with base change. Now here I would like to squeeze it a little bit. So that I only assume that the morphism is flat in codimension 1, and the fibers are Dubois in codimension 1. Sorry, codimension 2. Okay, so I can ignore some bad singularities in codimension 3. And I don't assume that the fibers are normal, but they have a, well, for instance, if they have Dubois normalization, but so the right thing to do, they are already Dubois outside the codimension 3 set. So you take this partial normalization, it's an isomorphism over the set that's known to be the Dubois, and you do as much of the normalization as you can over the others. Okay? Now that this implies that omega x over b is flat and commutes with base change. Now, of course, when you see this, then there are two questions of it. Well, sorry, first comes the surprise that we cannot show that OX is flat under these assumptions. We can only show that omega x over b is flat. But I could not write down a counterexample where OX is not flat. It would be quite nice to decide this. It would be useful to know that OX is flat. That would be the best. And so maybe what explains where sort of omega should be better than O, because omega it does not see non-normality when it happens in codimension 2. Yeah? So there is the finite morphism that's an isomorphism at all codimension 1 point, so the both on y bar and on y, then they have the same omega. Okay? And so that's why you have a hope that even though the fiber might have some bad stuff, might have some embedded points, or might have some non-normality in codimension 3, but the dualizing sheaf will not see. Okay, and in fact, that seems to happen in our case. Okay, so now, so what we do here is just to go back to the previous proofs that showed that omega is flat, and we just try to look, well, where can I chip away some assumption? So if you just look at it, so for instance, one thing you get, well, so you see, I need to prove that the highest cohomology group is a free module. And then if you look at the proof to do that the highest cohomology group is a free module, if you look at the diagram, I needed this surjectivity condition only for n and n minus 1. I need this surjectivity here, that this line I can ignore, and then the rest of the proof I just need surjectivity here, okay? And so you see, so that's why I have I have some hope that I can ignore the higher four-dimension thing, because if I have the highest cohomology group tends to be not affected if I mess something up in small dimension. Okay, so then sort of here comes the thing. So I have something y of few dimension, and here I take a partial normalization. So I assume it's an isomorphism in codimension at most 2, and so it's only a codimension 3 set that something changes. I assume that this is a homeomorphism. Okay, so think of it, I mean, so for curves, if I have a cusp and I normalize it, it's a homeomorphism. And if there are some embedded points here and I just remove them, then that's again a homeomorphism. Okay? And I have this assumption, which sort of comes from the previous thing. And I only then y bar is Dubois. Well, so then exactly this thing I need for nn minus 1 whole. Okay, and so why is this the case? Well, and so, okay, and so I'm afraid this diagram is rotated to what I have before. I'm sorry. And so this map here, well, since y bar to y is a homeomorphism, that this map is an isomorphism, yeah? And since I have an isomorphism in codimension at most 2, the highest 2 cohomology groups of the two things, they are isomorphic. Okay, you just write down the spectral sequence and then there's nothing interfering. Okay, but so now you ask the question, well, this is great, but I mean, will it ever happen? I mean, you know, if you think back on your life, you probably never encounter sort of this many assumptions. Yeah, that something, you know, the homeomorphism, isomorphism, codimension at most 2. You know, so people who deal with curves, of course, they don't know that codimension just 3 exists, and even surface people sort of don't really know that this can happen. Okay, so and so anyhow, well, once we have the semi-log canonical version. So if something has a semi-log canonical partial normalization, that is a homeomorphism, and the morphism is locally stable in codimension at most 2, then I know that omega x over v is flat and convoluted. Okay, but again, it sort of leaves open the question, where do you find things like this? Okay, well, let's see first what's the consequence of this. And so let's assume that this omega xk bar, this is in fact locally free. Okay? And so this is the case that we will use. Then the claim is that omega x over a is flat and locally free. The structure sheet is flat. Well, of course, this is okay because once this is locally free flat, and no x is flat. And then, of course, all the others, well, they are just locally free, and so they are flat. Okay. And so this whole morphism is stable. Now, I want to emphasize that I have an exclamation point here because this is not as obvious as it seems first. So if I have something that central fiber is locally free, then of course you say that it's locally free. But you see, this is locally free over something that's sort of larger than the central fiber. And so if the map from xk bar to xk is not an isomorphism, then the structure that if something is locally free on xk bar is definitely will not be locally free downstairs. And so you sort of need to think about this a little bit, and you need this as assumption that this map is an isomorphism in codimension too. So the once you are aware of this point, it's not hard to do that. Okay. And so I ask yourself how to make omega locally free. So that was the game. We try to take a cyclic cover that makes omega locally free. We applied the previous results and then we declare that we are happy. Okay. So, let's start. It's a general level. As U will be an open set, usually X minus a point removed if I do induction, where I know that things are already done. And so let the U be some scheme where I have this omega U to then, this is in fact free. Now then I can take this cyclic cover, and now then I take this omega U bar is free. How do we know that? Well, the push forward omega U bar, we had this formula, it's at the home of this, and now the I equals sum, and it has the identity section. So that gives me that thing. So at least this is the way I can get something. Okay. Okay. Now here there's a little bit of work. So see, I would like to prove that somehow whatever happens in codimension 3 does not matter. Now I use some induction on the dimension working locally. We assume that if I'm on the central fiber, then the M's power of omega is free, and stability holds outside this closed point. So that will be my U. Okay. Okay, now what's the cyclic cover I need to take? Well, so I need, and so I know that if I take this relative omega, and so for later formulas, just the minus M's power will be easier, you know, since M is free, so that these two are in fact isomorphic. But the minus M will work out simpler formula. They are in the kernel of the Picard group of U restricting to the Picard group of UK, yeah, because I assume that this is free, so if I restrict it to U, then this is, if UK is also free. Now what's nice about characteristic 0, and this is a problem that will haunt us in characteristic B, that the subgroup of the subgroup is a K group, is a vector space over C. That means it's divisible. So that means there's a unique line bundle L on U. So this L will denote this push forward to X, which is not a line bundle. I mean, that's our problem. Huh? Such that if I restrict it to UK, it's an isomorphism, and if I twist this omega with L, then the minus M's power will be trivial. Okay? So that means I know that it's trivial on the central fiber, and after twisting with this line bundle, the same will hold for the max. Of course, my aim is to prove that L is in fact trivial, and so then I'm in completely good shape. Okay, so now L is flat over A if and only if it is free. Okay, so that's how I will get that it's free. I hope to prove that it's flat. Okay, now I take my cyclic cover. Okay, and so what can I say about it? Well, so again, let's write here. This is my cyclic cover. Now the over UK, well, I have this cover, okay? And I have this map, which is a partial normalization. And in fact, this is a homeomorphism. Yeah? So out of this, I just have a homeomorphism. So this is where I will apply my previous theorem. So the only thing that can happen here is at the close point X, this map is an isomorphism over UK. But this YK might have embedded points or just might have some non-normality there. So I don't know what happens at X, but outside X over the phi. And now I had this semi-locanonical version of the P theorem, which says that omega y over A and OY, they are both flat. And now the push forward of y over A, this has a summand, which is just the home omega x tensor L omega x, which is just L inverse. So this is flat over A, hence it's free. Okay? And so somehow this thing just fell into place. So now once L is gone from here, then I get that these are flat. So then I have that these are flat, and all the summons are flat. You see, so that was all we have to do here. Okay, any questions? Okay, so then now comes just very quickly. So more or less, if you want to know what Dubois singularities are, so what Dubois wrote down originally. So he said that there's a filtered complex that computes the Hodge structure. Okay, and so in particular, if you look at sort of the zeros graded piece, and so the point is that this is not a sheet; this itself is a complex. Okay, then I have this rejection. Okay, and so then if I look at the things, what happens? So there is the cohomology group of the constant sheet. And now before that, I just used how it mapped into the cohomology group of the structure sheet. Now there's a natural map here, I mean, at sort of sheet level, it's OX maps here. In fact, the zeros cohomology group of this complex is exactly OX. And so there's a natural map here, okay? Now the right definition of the Dubois is that the map from OX to here, this is a quasi-isomorphism. Now this means that this map is an isomorphism, okay? But if this map is an isomorphism, and if this is surjective, then of course this is surjective. But so just because this is surjective, so we could not write down an example, but a priori it can happen. But so this map is surjective, but this map is still not an isomorphism. The group is sort of smaller here, so this is not an isomorphism. So it's easy to write down varieties where it happens and doesn't have Dubois singularities, but then once you start taking products and the hyperplane sections in the example, it's always failed at some point. But if you want to understand what Dubois is this, and then sort of what worked for the localized version, so you know, as I mentioned sort of before, sort of my incorrect definition of Dubois sort of worked only for proper schemes. If you want to prove something locally, then sort of the right statement is this. So that if there's an Artinian scheme with residue field K and either finite type morphism, it's very important is not assumed flat, so just a finite type morphism. And we assume either that the characteristic 0 and the central fiber has Dubois singularities, or characteristic positive and the central fiber is F pure. If you know what F pure is, fine. If not, just ignore this fine. And so then for every point and every I, this local, the maps between this local cohomology, they are surjective. So somehow this seems the right statement. So that means you have to go back to sort of everything we had before and sort of put local cohomologies everywhere and work with complexes. But this is how this will work. I think that's it. Thank you.